it's different when we can see the person, right?
Yes.
Then, just a thesis and you read and you like it and you ask questions. Oh, and lots of people are watching.
Yes. We will sharply start at 3 o'clock session.
Okay, so what do I do? I wait for you to tell me to start, right?
Another 2 minutes, another 2 minutes.
Okay. And I set up an alarm so that I will stop after 20 minutes for questions, okay?
Yes, ma'am. Yesterday, I informed Ramakrishna sir that today is your session, ma'am.
Oh, can I start or what?
Nagraj sir?
Yes, ma'am. Yes, ma'am.
A very good afternoon to everyone. Distinguished speaker, respected faculty members, researchers, delegates from various institutions, and my dear students. It's my great pleasure and honor to welcome you all to the International Congress on Industry 5.0, Human-Centric and Sustainable Future, a forum dedicated to exploring how engineering, computing, and interdisciplinary innovation can work together to create technologies that truly serve people, society, and the planet. Industry 5.0 represents a shift in perspective. It reminds us that progress is not measured merely by automation or efficiency, but by how thoughtfully we design systems that enhance human well-being, sustainability, and ethical responsibility. This Congress brings together diverse minds from artificial intelligence, healthcare, sustainability, and design to collaborate on solutions that address global challenges through a human-centered approach. Today, it is a special privilege to welcome a great researcher whose career perfectly embodies the spirit of Industry 5.0, Professor Claudia Maria Bazar Meridis. We welcome you. Professor Claudia is a distinguished full professor at the Institute of Computing, University of Campinas, Unicamp, Brazil, and an international respected leader in scientific data management, database systems, and data-intensive computing. With her PhD in computer science and the University of Waterloo, she has dedicated her career to advancing technologies that make complex scientific data accessible, usable, and impactful for society. Her pioneering research focuses on the integration and management of heterogeneous data from sensor streams and satellite imagery to clinical and multimedia data, enabling interdisciplinary collaboration across environmental science, agriculture, biodiversity, healthcare, urban systems. Though her work on scientific workflows, open science, and research data interoperability, she has empowered researchers to transform raw data into actionable knowledge that directly benefits communities and policy making. Beyond research, Professor Claudia is a visionary institution builder and leader. She founded the Laboratory of Information System at Unicamp, mentoring generation of scholars and establishing a vibrant ecosystem of innovation. Her service to the global computing community includes leadership roles such as President of the Brazilian Computer Society, Member at Large of the ICM Council, and the Council Member of the Research Data Alliance. Her contributions have been recognized through prestigious honors, including fellowships in the Brazilian Academy of Science and the World Academy of Sciences, along with numerous international distinctions. Equally inspiring is her commitment to inclusive growth and the empowerment of women computing, demonstrating that technology's excellence must go hand in hand with social responsibility. Her journey exemplifies what Industry 5.0 stands for: technology with purpose, research with impact, and innovation guided by human values.
Wow, thank you so much.
On behalf of the organizing committee, it is my distinct pleasure to extend my warm and heartfelt welcome to Professor Claudia Bowser-Milos. Over to you, ma'am.
Thank you so much. This was a wonderful introduction. Not even my mother would speak so well about me. Thank you.
Thank you so much, ma'am.
Thank you. It's a pleasure to be here. And let me start my presentation.
Yes, ma'am. Yes, ma'am. Sure.
Sharing my my screen. You can see my screen, right?
Yes, ma'am. Yes, ma'am.
Okay, so you've already introduced me. And a special thanks to you, to Dr. Ramesh Babu, and to all the organizers and all the people who are here in this audience.
Thank you.
I'm going to talk about open science as an enabler of Industry 5.0 practices. And these are keywords I'm going to talk about. And the main challenges of this enabling are the fact that we have to think about humans and design for sharing and collaboration. So these images, what they have in common, they are applications, they are research in which I've been involved with scientists from many fields. For instance, this is about IoT in agriculture. This is about interactions between insects and plants. This is about noise, urban noise mapping, climate change, and so on and so forth. There is someone with a microphone turned on, I think. So, collaboration is what led me to open science. And this is a key figure in my presentation, which shows what open science is about, which is about collaboration through sharing of every artifact, software, hardware, logs, experiments, publications. And sometimes you collaborate with people you have never seen and maybe will never see. Okay, so think about the key to that induces Industry 5.0 is how to prepare whatever you are doing so that you can collaborate not only with people and machines that are around you, but people and machines that are anywhere in the world and maybe who we will never see. So if you take that figure and expand it in the internet, you have a huge network of collaboration through sharing and in the world where one of the key ingredients is that arrows are not only one way, but they are two ways. The more you collaborate, the more you share, the more you contribute to knowledge, and you change things and improve them, and you innovate. And through that, you change the world. But the challenge in this, I'm going to share my data, I'm going to share my software, who are you going to share it with? How can you ensure how it will be used, when it will be used, and maybe the things that you make available that are part of your work will be used after you die in the future. And so how can you collaborate with people who are not born yet? And because all of us use information, papers, data, appliances, devices that were created very often by people who are not with us and maybe are already dead, okay? Like, I don't know, Einstein. And one of the advantages of this mindset of open science is that when you prepare for a collaboration, you have to document so that anyone can understand. And in this sense, even you will be able to understand in the future, in 10 years and 15 years and 5 days. So you are collaborating with your future self. That's an important concept of open science and of preparing for sharing. But it's easy to say and difficult to implement. How do you implement? You implement by storing everything you want to share in a repository. So the notion of repository is not a dead place like a disk, like a storage system where we store stuff. It's a digital service that is maintained and used by people. It's a live structure, which we can divide into a catalog and the files. And the catalog points at the files. And the files can contain absolutely anything. So think about open science as open and science and people. And the keywords are share, collaborate with whom? With people, with industries, with organizations, with robots. Why not? You have to do that. You have to document, and you have to be able to reproduce what you have done. Otherwise, it's worthless. You cannot reproduce, it's worthless. It will be reused. And also, one of the advantages of making things available is that what you produced is auditable. So the idea of why open science, the main ideas are advanced production of knowledge, enable collaboration by openly sharing everything. But the important thing is that there are many things that cannot be opened, okay? But you can open the description. Maybe not the files themselves, but the description of the files. You open the catalog. And this is called as open as possible, as closed as necessary. So an important issue are ethical and legal constraints. So how does open science provide framework for Industry 5.0 to prosper? Through the fact that it fosters interdisciplinarity and advances knowledge and innovation. So you already know that these are the main Industry 5.0 principles: human-centric, sustainable, resilient. And how does the collaboration ecosystem fosters that? Because when you collaborate, when you share, you also share your methods, you share your data, you share your software, you share your practices, and produces innovation. And please think about it as always, an arrow in which everything that is produced is improved through reuse and feedback. That's a secret that we cannot think about producing things for others. That's the first part. The second is their use and feedback will improve what you have prepared. And that's the secret we have always to think about. So think about the figure, people collaborating, but it's not only people, okay? You collaborate with robots, robots collaborate with each other, and they collaborate through the sharing and interpreting of files that are correctly documented. And again, bidirectional arrows. So the principles there are that you have to think about sharing and collaboration when you start designing a project. How am I going to produce results so they can be reused by robots or people I have never seen? When I execute the projects, I have to leave documentation of the execution so they can be reproduced. For instance, logs, the results are documented, and again, ethics and legal aspects. Now, this is all very abstract, so I'm going to give an example of what is called the FAIR principles. That everything you store in a repository must be findable so others can find, accessible so they can be retrieved, interoperable so they can be interpreted, and reusable. Oh, I have only 10 minutes, right? Anyway, 3 more minutes, I'll be over. The secret to think about it is metadata. So I don't know if all of you know what metadata are, but if you go to a pharmacy to buy pills, you do not open every bottle. Or when you go to the supermarket, they have to have labels. And the labels contain the metadata. What is the product? Who produced it? The validity of the product, sometimes ingredients, okay? So the metadata is data that are attached to data so that you do not need to open the file or drink the bottle here or the paint here to discover whether it's a juice or paint. So see an example? I look at this, it's a file. What kind of file is it? The metadata will describe. Maybe it has 50,000 lines. I cannot go through them all. This is a rainfall sensor data. Sensor ID, where it was collected, who deployed it was a robot, manufacturer, and so on, and the DOI, a digital object identifier for the data. The file is stored in the repository. There is a catalog that you go to the catalog from outside. I want to have sensor data, and the catalog will point to all files that have sensor data. And then you look at the metadata and find out what you want. And finally, who's the user? These are the users: people, robots, AI, software. And when you have user-centric, I brought this very interesting example of people in a village in Namibia that live in round spaces. and they only see circles. So if you present them with this figure, they will see circles. Can you see circles here? There they are. So there's been lots of tests with these people. The first thing they see when they look at this picture are these circles here. When you prepare something to be used, you have to think who the user is, okay? And that's being user-centric. Is a robot going to use it? It has to be translated into some language. Is it people who are not scientists? The language is different. So summing up, the main concepts: collaborator sharing. How do you enable Industry 5.0? You start preparing at the design of everything that you have to share. You think about FAIR because it will help document so things can be found and reused, and always think about preparing for the user. Thank you. These are the main concepts in the presentation. And now I'm open to questions. That's all. Thank you.
Good afternoon, ma'am.
Good afternoon.
Hello, ma'am. This is Preeti.
Yeah?
I have a question on
Yeah?
data storage tool, which can
Yes.
store up to images and video and could extract metadata out of it.
You can, the storage, it's something that is made available to you by an institution. And you can store anything you want in any format according to the storage unit rules. Okay, so in open science, there are different, that storage is called a repository, right? So you can store whatever you want, provided you are compliant with the rules of whoever has made that available. If you want to look at open science environments, let me, just a second, I'll just click on here, sorry, and I will just suggest something to you. Just a second. Look at something called Zenodo, which is a generic storage system where scientists can store anything they want, up to 50 gigabytes, okay, or fixed share. And these are examples of world storage facilities that let you share anything you want for free, as long as you provide the metadata. Does that answer your question?
Thank you, ma'am. It was really good to know that there are two softwares which are open source and the researchers can easily use it. Thank you, ma'am.
Oh, okay.
Dear students, any questions?
So just to continue, if you are with, just a second, let me go again. If you are interested in open source, look at software heritage, which is a huge a huge storage system that collects all open source that's produced in the world. It is very interesting, but I cannot show it to you right now, but it has several billion files. You cannot deposit in software heritage, but if you deposit in GitHub, for instance, it will collect your code and make it available to anyone in the world. Okay? Take a look at it.
Noted.
And if anybody has any doubts or additional questions, you can always email me. Rohini knows my email.
Yes, yes, ma'am. Sure, I will share the email.
Yeah.
Yes, ma'am.
Yeah,
Yes.
Professor, this is Dr. D.R. Ramesh Babu.
Hi.
Hello, good afternoon. Thank you very much. It was a wonderful talk. And I just have one question that many of the researchers wants to pursue their research in medical image processing or
Yes.
on medical field or healthcare. The challenges is, to get the data from the medical equipments, we have to have a lot of ethical clearance from the medical school. So that was the challenges we are finding very difficult to collaborate with medical school and pursue our research. So what
Yes.
is your suggestion for the young researchers to carry out research in medical or healthcare field?
Well, there are, one of the main problems, as you mentioned, is and which is maybe the most important problem, is ethics. Okay, so to handle, and the second problem is that depending, as you very well know, on the imagery devices that you use, you need special software to understand it. But I don't want to talk about the technical. I'd rather talk about how we are handling the ethical issues in my university and in many other places that are working in this kind of research in the world, if you want to share and make things open. Our terms of consent have been changed so that the patient, when the patient signs the consent, the patient says that the data, if anonymized, can be reused and open for research. Okay, so we changed the consent terms. And the other thing is that if we manage to anonymize the data, then it's easier to share. Otherwise, you can always provide the metadata saying the data belongs to medical experience. It cannot be shared, but please contact me if you need more information. And that's in the metadata. Okay, and through that, many researchers, that's not only here, I mean, it's all over the world, through adding in the metadata. My data are not open, but please contact me. In my university, we're starting lots of international collaborations on medical data just because this clause is added to the consent or the clause is added to the metadata. I hope you
Yes.
can email me afterwards if you.
Sure, Professor. Yeah, I got it. Thank you so much. Thank you very much. I
You're
will be in
very
touch with you. Okay,
Nice
if
to
any
meet you.
data sets or any collaboration, we'll be eagerly wait to collaborate with you. Thank you so much. Yeah.
That would be wonderful.
Okay, any questions? Okay.
I have a colleague who works a lot with doctors, and clinical data. And I also work a lot with clinical data. And some of my colleagues work with medical imagery. So that would be wonderful to be able to collaborate with people in India about this. Oh, I'm sorry, I didn't want to interrupt you. I talked too much.
Oh, thank you, Professor. Thank you.
As we come to end of the insightful session, let us take a moment to reflect on the key ideas and inspiration we have gained today. The discussion has clearly highlighted how Industry 5.0 is not only about advanced technologies, but about placing humans at the center of the innovation. We have also seen how open science fosters collaboration, transparency, and shared knowledge, enabling researchers and industries to work together toward meaningful and sustainable progress. We are truly privileged to have had an opportunity to learn from Professor Claudia Bazar Medeiros, whose remarkable contribution to open science infrastructure, scientific data management, and global research collaboration exemplify the value of human-centric and socially responsible technology. Her work reminds us that innovation achieves its true purpose only when it benefits society as a whole. I sincerely thank our distinguished speaker for sharing her expertise, experiences, and I also extend my gratitude to all participants for your active engagement and thoughtful discussions.
I thank you so very much. And afterwards, I liked a copy of this recording because you have been a wonderful moderator. And I loved your introduction and your conclusions. Really, thank you so very much. And thank you to everybody who's here. It's a pleasure.
Let us carry forward the ideas shared today, continue to collaborate across disciplines, and strive to build a future where technology and humanity grow together. Thank you all once again.
Thank you. Goodbye.
Thank you, Professor. Thank you very much.
Thank you to all of you. Bye-bye.
Have a wonderful day.
You too.
Yes, ma'am. Thank you.
Dear
All the participants, please be wait. We have the next session at 3:45.
Hello, ma'am. Preeti, ma'am. Am I audible?
Yes, ma'am.
Okay. Thank you. Thank you. Yes, sir has joined. Good afternoon, sir. Sir, you are not audible. Yours is muted. You have to unmute.
Yeah, my voice audible, ma'am?
Yes, sir. Yes, sir. You're audible, sir, now.
Yeah. One second, ma'am. I just share the screen.
Yeah. So before that, I just formally introduce you, sir. I'll just take 2 minutes.
Yeah, sure.
Good afternoon, everyone. Today, for this session, we have an eminent speaker, Dr. Radhakrishnan Delli Babu from VIT. He is an academic and researcher associated with VIT. He has contributed to teaching, research, and academic development within his field with a focus on advancing knowledge through scholarly research and student mentorship. His academic interests include areas within computer science and engineering, encompassing both theoretical foundations and applied research. His work reflects engagement with contemporary technological challenges and the application of computational methods to solve real world problems. He has authored and co authored research publications in peer reviewed journals and conferences, demonstrating ongoing scholarly activity. In addition to research, he is actively involved in teaching UG and PG courses and supervising student projects, contributing to academic capacity building and skill development. We are very happy to have you here, sir. Over to you.
Thanks, ma'am. Thanks for introduction. So give me 1 minute.
Yes,
I
sir. Yes, sir.
download it. Yeah, hopefully you can see my screen.
Yes, Professor Radhakrishna. Yes.
Yes, sir. We are able to see.
Yeah, thanks. Okay, thanks for inviting for this wonderful event. Yeah, today I'm going to talk about how quantum machine learning can do it in the Industry 5.0 applications. So it's a very generic talk. I think this is an online talk. If any question, doubts, please unmute and speak. We'll give you a clarification for it. Okay. Yeah, this is an outline of today, my talk. I'll give you what is the Industry 5.0 and then what is quantum computing foundations and how quantum machine learning can apply for it in the aspect of Industry 5.0. What are the key QML algorithm can support for the current era? What are the applications for in Industry 5.0 and challenges? And I can conclude this talk. So, ma'am, 20 minutes, how much minute, ma'am? 40 minutes, my talk?
We have planned each session for 20 minutes, sir. And
Whenever you give me a flag, ma'am, because I have a lot of slides. So let me know. Okay? Sure.
Yes, sir.
Yeah. So I kick start now. I think today the session start today. Everyone know Industry 5.0. So I'll give you the picture. So Industry 1.0 is like clearly this like steam powers and waving looms or whatever this very beginning era. And 2.0 is a mass productions and assembly lines and electrical energy. And 3.0 is automations and computations, electronics. This is 3.0. 4.0 is clearly that IoT and networks, cyber physical systems based on that. 5.0, currently we are in, the people are calling even 6.0 will go in future. But 5.0 we're talking now. So human-centric, so that's clearly that how human and centric all the thing. Sustainability, very interesting one for the good point, sustainability and realization. So these all three categories can go for 5.0. Okay, so how the three aspect of apply for quantum machine learning can apply for in the goal to achieve Industry 5.0. So that's today my talk. So you know that clearly that define the Industry 5.0. The core principles, Industry 5.0 is not just a technical upgrade. So clearly that's not technical. It's a value-driven shift. Okay, it plays the well-being of the working at the centric of productions, processing, and use a new technology to provide this. Based on that new technology, provide beyond the jobs and growth while respective in the production line of the planet. That's clearly that part of shifting for not only productions going the next level. Okay, clearly this is a 5.0. So clearly this is a definition. So you know the three pillars. Okay, first thing is human-centric. Okay, adapting the technology to human needs, not vice versa. So that means technology to human, not human to technology. So that's clearly that understand human-centric. So that's clearly sustainability. You know, you know that this is very important for milestone goals for sustainability. The circular economics, energy efficiency, like a waste management direction. So this all come from sustainability characters. So that's clearly there are 17 plus something. So clearly that one for come from resilience, clearly robustness for against the disturbance. That clearly that's pandemic or climate or geopolitical. So everything come from this part of this robustness against. Okay. So three main pillar for Industry 5.0, how to apply for our perspective for quantum aspects. Okay. So you need to get understand. So 1, 2, 3, not a big deal. Okay. So 3, 4, something similar for computing grams. That's why I say that you can say quantum 4.0 to 5.0 difference. So what is a different scale? Then you can understand much clear for Industry 5.0. So what is focus? The focus come from efficiency and protection, like clearly that 4.0. But here, not only efficiency protection, but you can say well-being and sustainability. So even go further. Okay. So that clearly. Human roles, clearly they supervise for the mission. So that's 4.0. But 5 point, collaborate with the robots. That's a co-pilot. So that clearly that you don't want only for missions supervising, but you can say collaborating that with the robots also. The goal is clearly that mass communications. So clearly that we get productions go on mass productions. But here, hyper personalization, because what exactly you want and how to achieve for the future, based on that, the threshold can maintain. Energy, clearly that Industry 4.0 is based on mixed thing, but clearly Industry 5.0 is clearly renewable energy, the green computing, whatever. So the especially you were talking about even the deep learning or quantum, whatever, the carbon efficiency. That's clearly the green computing is efficient for 5.0. Okay, maybe 6.0 we'll come back. We'll talk about it later on. So that's next era. Okay. So what is the role of AI industry? Because I'm from computer science background. So what exactly AI can play in the 5.0? Okay, that's clearly to understand for the theme of talk today. Okay, so I said clearly that the AI can picture for collaborative intelligence, like based on that AI argument, human decision making. That's clearly that human take decisions based on that AI will part of it. And predictive capability, because based on that failure occur, then what occurred failure before you can anticipate. Okay, because of maybe predictions you can make it before and then get solve everything for in while time being. And generative designs based on that creative sustainable materials and structures, because clearly that given the materials should be a sustainability, because clearly that's very important for reusable things. Okay. So three aspects for the AI can play in the 5.0. One for collaborative intelligence, predictive capability, and generative designs for this based on that. Okay. So some limitation must be there. You put some threshold, always limitation. You cannot do something beyond. So what is limitations? Classical AI struggle with the complex molecular simulations. And this is very important because drug discovery is a very big problem nowadays for the from AI perspective, and vast computational optimization problem, because clearly that because why is very important, personalization medicine is also a big problematic. Okay, so even every human have different neuron sections, how one medicine can be applied for everyone. So that's come from drug design, very famous. Okay, so that cannot solve the current era. That's why we want to go to next era for quantum. So that's clearly this picture. We want to go for this the method to implement for quantum. So I said clearly, why quantum now? That's clear questions. Okay. So because Industry 5.0 clearly picture is there, three pillars. So why quantum can apply? What quantum can apply to get the answer for it? So first thing is the quantum picture is, you know, that Feynman, he talk about a very interesting story for quantum 1.0. So whatever I am quantum people working means I am 2.0, like a post quantum era. So like a PQD, something like, okay, it's the 2.0. We take a knowledge for quantum and apply for my knowledge to the quantum too, and done for my problems. Okay, that's the 2.0 aspect. First thing is Moore's law. Always we'll say that Moore's law is the first thing. What first thing is? Suppose you design a chip. So the transistors, because currently we are working on 0 1s. So based on the transistor, okay. So transistor you can say you can just make it a mimic going down. maybe you can say that now transistors are even small size also, because very small, tiny size also, but you can't make it nothing more to develop more. So that means surely that Moore's law will fail. So transistors increasing and slow speed is decreasing. So that means you can say that now clearly that the proportion between speed and transistor is sometimes end with the error. So that means you should be more than 0.1. You can apply for something in better than the competition field for the next generation. Okay, that's come from quantum. Quantum apply for these different aspects. So Industry 5.0 problem, I said clearly that very challenging problem for drug discovery and climate modeling. That's clearly that one more challenging for climate. Currently that, in my place, Tamil Nadu, okay, so every, that Sankranti event, Taipusam, I mean, Tai. So always, whenever we do with a different procedure for farming, always hot weather, okay? But this time I can't even stand out because it's too much cold, because climate changing, I don't know why, how this all question will solve for the powerful company will solve it. That's maybe quantum, maybe. So that means especially hard to solve, but maybe it's solved for quantum, maybe different aspects, okay? And very interesting one thing is quantum supremacy. That's very interesting one. Solving a problem in intractable from the classical chemistry. That's very important. So because of it was something problem to solve, some I complex problem to solve in the classical, it's sometimes problem, but you can go with the other level, not only 0.1, something other level to solve the problem with the classical to quantum. Okay, this one we are going to use for quantum. Okay. So I say clearly there's this aspect to do for quantum era. So now the question come from, I give you some bit understanding for what is quantum algorithms, and I'll go for this different aspect. Okay. Already I'm not going for deeper quantum, but I give a very simple idea to understand for you. So classical, everyone know that either 0, 1, the 0 bits are 1 bit, true or false, and deterministic. Clearly you can say either 0 or 1, that clearly. But quantum bits, there is a matter for alpha 0 and beta 1. I mean super gate. I mean Brown gate. So based on that superposition. Okay. So that means alpha beta some complex number. So then alpha square plus beta square equal to 1. So that means 3 dimension. Right? We can come to that 0, 1, some other things. Maybe a true, false, maybe other dimension also. That may come from 3 kind of that come from superpositions. So for example, superposition means either not only 0, 1, maybe other position also. Maybe parallel you can apply for every positions can do it. Okay, so that's called superpositions. Make it for it. Okay, that's one thing. So for example here, so either 0 or 1. I said now clearly this 0. I can make it 0 or make it 1. So that Sai saying that maybe the position come from here also. So why is the matter here? Maybe that always when I toss a coin, the coin tossing is either head or tail. The two aspects come. The probability come from either head or tail. So maybe my questions come from while toss a coin, the floating that happened. So wherever the floating time, what time now head or tail? So that may be a matter. So that measure it the time. While measuring the time, it may be different aspect, different positions must be there. That come from maybe the superposition. Okay, the state come from superposition. Okay, so that's a state come from the state come from this position of how to measure it. Alpha 0 gate plus beta 0 1 gate. So based on that, where the position come from, alpha beta. Okay. Now I said clearly that what is the superpositions, how to generate with the classical one to understand simple. A system have n classical bits can represent one state out of 2 power n. So clearly that 2 bit mean 2 power 2, 4. Okay, so that means clearly 0, 1. So 1 mean so still 2, 2 power 1, 2. That means 0 or 1. So make it 2 means 4. So 0, 0, 0, 1, 1, 0, 1, 1. So the 4 bits. It's always 2 power n states. So the main question is one state at a time. Either 0 or 1. Either 0, 0 or 0, 1 or 1, 1 or 1, 0. Either one states. But when you go for the system with the n qubit systems, that's a superposition, because it says now we are in superposition states. I can access all the states simultaneously. That's very important. For example, I toss 2 coins. So when I toss 2 coins, maybe 2 head, 2 tails, 1 head, 1 tail, 1 tail, 1 head. So that means 4 positions. That means 2 power 2 means 4 position Wilson. So when I say classical, I take either at one states. Maybe either the 4 states, I take only one. But here in quantum state, the quantum qubit saying that I can access 4 states simultaneously. That means what 4 states means? I toss a coin, I can measure it on the flow on the states executing. Okay, so then I can access all the states. That's a one powerful for quantum. Okay, it's called superpositions. Okay, so what is the mean for it? It's a parallelism. So operation can be performed on the all states at once. That's it. All state once, because clearly you can say all states can be done with this states. Okay, that's superposition. So, you need to get a 2 points for who are sitting in this lecture. So, if you have physics, please forgive me because I am a 2.0 guy, like a Zen guy, you can say that. Now, I can say I want to take only for what is the logic, quantum logic, what is superposition, what is entanglement. That's enough for me. I can frame my problems. How the problem, that's we can say today. Okay. So, the entanglement, one more key pillar. So again, this is nothing much useful in our machine learning, but you need to understand this very good theory. So Einstein said spooky action at the distance. So that's clearly this is the matter. Okay. Two qubit can be calculated such as the states, or one instance determine state with the other. For example, I toss a coin here. It's come from head means other states, other qubit can put it in the other galaxy also. It's be a tail. That means opposite. You can say that without distance, it's opposite angle. For example, here head means here tail means head. So that means reverse. But you can't make it a reverse things. But only this action happened. How it happened, we don't know. There's experimentally people are doing for 200 kilometers, 300 kilometers doing. But China, people saying that they done for galaxy to moon, but there is no proof, but people are calling. But people are, this is possible. This is working on it. Okay. So that's clearly working on this actions. Okay. So how they're doing, we don't know. So they're doing eventually done. Okay. So that's come from this very interesting topic for that's quantum teleportation and density code. So, you know that this Nobel Prize this year also teleportation thing. So that's clearly that's quantum era started always. Okay. So enable strong correlation between this quantum neural nets. That's a very interesting one. So how to do it? This one based on that connections. Okay. You know that input layer, some hidden layers, output layer. So that surely, so input and output, two are entangled. Okay, the two are things. So based on the distance, some sort of neural nets. So surely it will be get some answer. So that's clearly we can apply this the method to apply in neural nets. Okay, so that's clearly that will happen for quantum neural nets. Okay, clearly that. Okay, so that means what you can see. Superposition one pillar, other pillar is entanglement. Two things very important to get rid of our quantum things. So how to get the quantum gates? Okay, you know the classical gates means everyone know and or not. So classical gate and NOR, XNOR, or XNOR. So they all surely that simple classical gates. So quantum have special gates. They can say poly X and poly Y and poly Z Hadamard gate. So there are different gates there. So I'm not going for deeper. So poly X is a NOT gate. You know the NOT gate surely clipping. So if it's 0 means 1, 1 is 0. So clipping is come from poly X. Poly Z is come from changing pace. Okay, for example, the pace come from the top angle. I mean, 180 degree means it's going to 280 degree. I mean, 38 degree. So surely the poly Z come from dimension changes. Okay, that come from poly Z. So and poly Y is also there, but I'm not going here. But Hadamard gates come from superposition. So poly X, Y, Z are very basic gates. Hadamard gates, CNAT gates, the two gates is there. Hadamard gates come from superpositions applying. What superpositions? X come from 0 or 1. The simple logic, flipping the coin kind of things. Okay. But superpositions clearly here. So I can put a 0. I can make a superposition. What superposition? I can access two states simultaneously. I can access from 0 states. I access for one state simultaneously with some probability. That's come from superposition. That's come from Hadamard gate. They do it. Okay. So now CNOT gate. So CNOT gate come from entanglement gate. So that's clearly that control NOT gate. So flipping the targets qubit if control is if the control for qubit is 1, for example. So 0 means I put a 1 control. I said clearly that flipping. 0 means 1, 1 means 0. So flipping this thing. They come from this surely CNOT gate doing for it. So that's clearly that essential for creating entangle. So it's clearly entangled states. You can imagine this. Okay, so you put a two galaxy, you put a one number here, other number will change automatically. Don't worry about number of distance, not a matter. Okay, that's called universal set gates come from. I said clearly that the gates come from Hadamard gates and CNOT gates very important for to get a simple quantum gates scenario. Okay, so again universal gates come from single based on rotations come from the rotation come from this 380 degrees Celsius. You can go for angle, you can do it, or plus CNOT we can apply for it, you can get answer for it. So I'll give a simple understanding for quantum circuit model. It's a Bell states. Okay, Bell state model. You could put a 0, 0 or 0, 1, 1, 0, whatever, that's your choice. I put Adamant gate and CNAT gate. So it's come from, so Adamant apply for superposition, CNAT gate mean get the answer for measuring for it. Okay, this come from Bell states. Okay, this is Bell state creations. Why Bell states? You want to make it a measurements. So again, it's a matter, a lot of challenges there. I'm not going for deeper because if we talk about more quantum, it's more and more. So measuring is a big problem. Error correction is a big problem. So there are plenty of things there. But anyhow, theoretically working something, but experimentally people are still working on Google, IBM. There are many people are working on huge money put and working on it experimentally. So there people are working on it, surely. So I said clearly measurements. The measurements clearly the picture of it. Okay. So I said clearly what is measurement means? To think about measurement means I toss a two coin. So flipping the coin, I can say in the top I can measure it. So measurements I can stop that coin. What exactly states it is, that's measure. So once I measure, maybe that they will change. So while measuring that point only that you can read this data. After the coin change also, the states also change. Okay, so that's a big issue. The collapsing, that big issue. That's why when extracting the information collapse the superposition. That's I said collapsing means I said clearly this the position is there. I can read this what value, but next second they can change collapsed. Okay, because that's why whenever measuring, we don't know how the machines come from answer. We don't know. So there are a lot of challenges in quantum, but theoretically yes, they can proven. Okay. And logically, yes, because IBM, Qiskit, they're working, many things is working good, but logically working, but physically people are not started, but they will start it. So result in probabilistic based on amplitude, because of clearly I said alpha square, because clearly that if you say that now, I can make it a two different entity, alpha square and beta square. If you put together, it's one. Otherwise, the problem is third position is problem. I say everything is probability. So the probability measurement should be one. Like a P plus Q equal to 1. It's a simple school college thing. Probability of success plus failure equal to 1. Same thing here also. You put the threshold here. Alpha square plus beta square, any angle position should be 1. Otherwise, you cannot solve the problem for real-time scenario. Okay. So we must run this circuit multi-time without disturbing for this measuring and we get a simple answer for it. Okay. And I don't know, no cooling theorem is there. So that means what you cannot reverse anything. So that means, for example, when you go to the simple classifications, simple classical one, you put a 1 AND gate, 0 will come. So you can 0 apply for AND gate, 1 will come. So that means simply that is clone. But here you can't non clone because why? Surely that the state will not get again. Because this measurement once measured, you can measure it again. So that means no clone theorem applies. So fundamental limits is there. It is impossible to create an independent and like a identical copy for arbitrary unknown quantum states. Clearly that's unknown because clearly the state is on the time you can measure it, we don't get again same state. So that's classical error corrections code does not work directly. That's why the error correction is very big challenging in quantum. Okay, so then this is all a matter for it. Okay, again this is called quantum error correction. So something will come up. So our goal is, I said clearly, because you are sitting for Industry 5.0. So that is very basic now. So quantum, simple, what is the things? And then now we can come to it, quantum machine learning. So the next thing is quantum computing. We talk about quantum states, different states. Machine learning, everyone knows. So machine learning is we give data to find the pattern to predict this. So clearly that, and then this is how to apply with the quantum computing. That's a very interesting one. Okay, so this is a new research people are working on last five years. Okay, so using quantum processing to isolate for ML subroutines or some linear algebra can use for how to apply for this simple quantum processor. Okay, using classical machine learning to improve the quantum error correction also the people are doing, and this today focusing on variational quantum algorithm. Why you want to do it? Because of this all thing apply for Industry 5.0. So that's the overall goal. I want to introduce this some algorithm. This algorithm can introduce for Industry 5.0 to help in the future. Maybe the era will come out. So I said clearly VQC, it's a NISQ, that is noise integrity era, because everything noise. I said clearly the era, because you need to remove the error for noisy. That's a very clear one. So we are still working on noise devices. Okay. So how to do for noise era? I said clearly that to understand, simple understand. Suppose I have a classical system, my laptop there. So don't worry about that. Your laptop cannot change. Your mobile phone cannot change for until some decades. Okay. So that means whenever I want some quantum, we can take a process. Otherwise, we can work on classical. So that's my hybrid mode. What hybrid mode? So classical CPUs, for example, I can say image processing. I can do some image to optimize this image to find out this predictions. So I can apply for the image processing to that quantum level. How to do it? I can do everything in the quantum level, I mean classical level. Whenever I want to make it for future extraction, like the future extraction part, I can do it quantum. Because when I do it in classical, each and every time one feature will take. So when I apply for quantum level, so it is I said earlier, parallel you can take all the features. It's a complex features. Okay, that is a very important for the future extraction part. So that future extraction I can give to quantum CPU, get some answer and take the value, exact value, and give to classical. So that's hybrid mode. You cannot work everything in quantum, but you can do it classical as well as quantum together. So that's clearly. So this is one I said clearly, nice intermediate scale quantum. That's noisy. So that's era come from noisy era. So based on that noisy intermediate scale quantum. So I think there are many experiments there. I skip on all the things because I'll go for the talk mostly on Industry 5.0. Okay. So there are different aspects. I'm not going for deeper. So if you go to a data encoding, how data encoding? So basic encoding, like a binary string to the basic states, and then amplitude encoding, n feature to log n. That's very important. So you give n features into log n qubit. See now, it will be synced efficiently, but hard to prepare. That's clearly the complex, but it's easy to do it in quantum. So, but classical not possible. So again, angle encoding, that is again rotating. Because I said you can say the features not only for, so for example, if you give a dog, give some couple of dog to the image to make a preparing for predictions. So pre-processing, I give each and every layer, 10 layers, each and every one features. For example, eyes, nose, whatever. So what I do, everything I apply for not parallelly, serially we're doing. Okay, we do everything classical serially doing, but when you go to quantum level, everything parallel will do it. Very fast efficiency. Okay, we do for it. Possibly you can do for retrieve very fast angle to get for it. Okay, so why the angle? Because I said clearly the first figure, I give a rotating angle. Not only 0, 1, we can angle it for 360-degree. We can make it a data from this. Okay, and there is a parameter. We don't go over much for this quantum machine learning. So there are two rotations, Y rotations, Rx, Ry, Ry. We can rotate whenever you want. We can rotate from 180 to 360, 360 to 180, because based on the rotations, we get a good answer for estimate good answers. Okay. So this is a quantum world, because the structure come from quantum world. Once you apply for this superpositions, that's a quantum world. Okay. So that's clearly this. I'm not going for deeper. That's still research there, but I'm not going for deeper. So this is surely it apply for get answer for it. That's not a doubt on it. Okay. So there are different aspects. I give a simple question for classical, I mean quantum thing. We can go for quantum level for different aspects. Quantum SEM, quantum do different things. Okay, maybe CNN. You can do RNN. Everything you do for quantum level. So how the doing? How the kernelization? That's very important. For example, classical SVM, the kernel tech is very important. So the SVM, support vector machines, you need to find the classical things. You can find this middle layer. You want classically, you can say true or false. Find like all the slack variable. You can adjust the slack variable based on that our data sets. Okay. So suppose you have a 10, for example, 10 slack variable, you need to adjust for 10 slack variable in one by one. Take one variable, I can make it closer to where exactly the data will come. But now you apply this to the quantum level. I give 10 slack variable to one time. Okay, so you can say superposition time. Then exactly where the line between this the two classifications. Okay, so the time is very fast to execute. That's the kernel tricks. So how to do it? The doing a very simple scenario. The quantum will map data into the exponential Hilbert space. I'm not talking about Hilbert space. Yes, that's one more thing. So when I say now, the space come from the machine learning come from simply when you give data. I can find the distance come from Euclidean space. So that means two data in the flat. I can take a data from x1, x2, y1 or 2, find the distance. I can say the distance between the two angle. I get a simple Euclidean distance. Okay, simple. But when you go to quantum is complex. I said it's a bowl because round. The complex. So complex numbers you apply come from Hilbert's. There are different spaces there. Euclidean space, Hilbert space, Banach space. There are different space come from. Okay, so we take a Hilbert space. The complex number can be applied for it. Okay, so the complex numbers there, you can Hilbert's space naturally. We get a data. Data should be a plotting in this curve. take the two data and find the square it and get this real numbers. So that's kernel tricks, very important for very fast go for SVM perspective. Okay. So the Baryon clusters, that's very, very interesting one. Gradient points. Well, you know that there are two aspects come from, you know that in simple mislearning, the convex problem, non-convex problem. That's clearly that's convex problem come from lot of local minima will come. But non-convex problem, sorry, the non-convex lot of local minima will come. You can't find the global minima. Global minima means which is minimum error. You cannot find. But the gradient thing is you can find the convex problem. When I go to convex problem, it's simply the slope is very complex. Okay. Then you can go to simply you can get a global minimum for the value. So the gradient easy to do for machine learning. But this is only for simple for Euclidean phase. But when you go to that quantum level, this gradient point is vanishing. Why? We cannot make a smoothing. Smoothing is a very big challenge in quantum. Again, this is a big one of the big problem in quantum level. The quantum circuits, the gradient of best cost efficient functions, it will be impossible to get it for it because why? Maybe it's complex. Maybe it comes from data should be everywhere in the space. So taking the nearest regions to finding is one of the key challenging. But there are solutions there, but people are still working on it. Solution to make a merging together. What solution? There's a local cost function. They make a loss function. You know that output and input to find the square, how much you lost there based on the loss function. You can find the loss. We can say local cost function to based on that. And then layer wise, each and every layer, how much loss we can make it for it. So there are different aspects to solve this problem for gradient vanish functions. I'll give you one example to get idea. There are different aspects. I said the various quantum algorithms there and various quantum eigensolver. That's again this one more thing, eigensolver. So if you give a different aspect of features in the space, okay, how to drag from the space for the correct features? So that's a question mark. Okay, so that the kind of problem you can say VQU. That means various quantum eigensolver can solve the problem. What's the thing is find the minimum eigenvalue based on Hamiltonian H because based on this angle moment you can easily find out how to do it. So initialize the parameters and then why this not converging the doing until you can do it in the repeating states. How to do it? Preparing states, each states apply to keep quantum process unit to measure it. When I say measuring means Hadamard gate. Okay. When to measure it, when I'm measuring for two states and find this classical based on the classical things and get the answer. So that means clearly you get two simple states you can measure for it. Okay. So this is come from why two states? It's come from Hamiltonian's. The Hamiltonian come from the short distance, not long distance. So whenever the data set be very short, you take the data sets from the two data sets, you can find same thing, Euclidean kind of thing, but different aspects. Okay. That's why Euclidean, I cannot put Euclidean. Euclidean would means short, but it's a complex. That's why Hamiltonian. So if you go to long distance, you can short from this based on this given this data sets. Okay. That's why you can apply for Hamiltonian state for to get the simple exercise. Based on that one, we can find the two distance and get this answer. We find this future extraction from the simple scenario. Okay. So again, quantum support vector machines. So there are many things. I skip for it. I'll go for the main picture. So they're looking, and then quantum neural nets is possible. And then, yeah, this again, see that now you're shifting from, you see that now we are shifting from classical thing to quantum level. Even classical hidden layers to quantum level. So that's shifting from the different space. What's shifting here? Without this get affecting for everything is easy. How to do it? For example, you go to integrity because you can go to you can do a partial differential equation df by dt because f is come from this finite difference equation for getting this two angles. So f of theta plus s. So theta come from the angle moment. S given this target, given the target values minus f of theta minus. So the two states. Where two states, I can make it a Hamilton distance between these two different paths. Easily get the difference between the two pitches. Okay, that's why the shifting is very interesting, and this is happening for the clear picture for the quantum level. So we are waiting for quantum hardware, how to do it, because I'm talking about everything is logically, we're working on logical qubits, but working on classical physical qubits, we are still waiting for the time, maybe 2 decades, 3 decades, surely we'll get it for good quantum computing will come. Again, optimization problems, this is our role model. So quantum optimization problem, because for example, that using for MassCat, because you apply for anything. For example, all classical problem, can go to quantum level. Okay, pretty sure. Even the quantum problem can go to even quantum AI level also. So that's also possible. So that means what? Every problem can go to quantum level, but the results efficiency depends upon the problems. Okay, so that may clearly say that now. So that clearly the picture is machine learning. All the machine learning. I'm not saying all. Most of the machine learning problem can go to quantum level. Most of the machine learning can go to AI level also. So in this case, such that we'll go that now. Very interesting for the Industry 5.0 one for logistic and supply chain. The very interesting problem. Okay, because this is all optimization problem. Like for example, you know that travel salesman problem that's come from logistic problem. Okay, how this the simple graph theory. Okay, so that's logistics problem. So that's how to solve this problem to Industry 5.0. So Industry 5.0 means I say clearly quantum can help for it. Okay, so alternate between this problem to Hamiltonian to mixed Hamiltonian. That's clearly this problem can be a mixture of Hamiltonian things also. So again, GAN problem. GAN very interesting. I have no time now. So the GAN problem is also that they're working on different aspects. For example, the complex probability distribution for quantum states, like financials or quantum digital twins. So they're working on GAN problem for working on quantum GAN, working on all the problems. And quantum CNN, very interesting problem. I think I have a couple of papers, this quantum CNN papers, so maybe you can refer it. So I'll go with our main motto. So again, federated learning, very interesting one for federated quantum learning. So the combined Industrial 5.0 privacy 2 with the quantum machine learning also. How to do it? Distributed quantum sensors, training a global model without sharing a raw data. Very interesting for federated learning. So quantum sensors, very interesting. So that's maybe a future. Quantum internet, quantum, there are many things will come in the future. Okay. So again, that's futures will efficient get a good results in the future also, especially for healthcare. Okay, because of each and every people health record is a precious. Okay, you can't give all data to that server. We can give that logic. Okay, based on that some formula logic, based on the assumption, you can put a blockchain, and then you can apply for quantum sensor. Easily can track for everyone in the world. So that's easy to protect your digital record, I mean health record in the future scenario. Okay, that may be possible for federated quantum learning also possible. So HHL, there are many. So I'm not going for deeper. So there are different algorithms to help for quantum levels also. Okay. So now questions come from. So this is a one converges because clearly. So you talk about whatever talk about. First I talk about quantum basic one. What is quantum machine learning and what are the different algorithm types I can solve this problem. So this matter how to help for current scenario for our today conference scenario. Okay, that's the question. So how to converge for all the things? Clearly that where does quantum ML can meet human-centric sustainability. Very the basic point, the three pillar, remember. The first pillar, human-centric sustainability, how this happening for this QML. So first thing is I say clearly, so material science, I say clearly that material science for sustainability, for designing that like this, so clearly that the given the design should be a lifelong learning kind of thing. Stronger materials, that's clearly that sustainability will picture the very much picture. Drug discovery, I said clearly personalized medicine, very interesting one. I said every neurons are different, how we want medicine. So the personalized medicine is one of the key pillar, that's human-centric. So that's clearly human can control this thing, human-centric things. On logistics, very interesting. I said already carbon, so carbon efficiency. Okay, so that's again one more thing. I come from energy efficiency, wrote the automation problem. So that clearly logistics is very important. Where, for example, there's a lot of company working on logistics problem. So they are working on quantum levels for how to minimize this optimization problem for the current era. So clearly this quantum machine learning can help for all aspects for the scenario. Okay. So there is other aspect. I will go for one or two. So we can go for one for digital twin. So how this digital twin go for Industry 5.0? So the challenge is like a simulating a complex multiple physics system in the real system. For example, you can do system with a complex system. We put it in QML base. Time is up. Okay, some questions come from. Okay, so the QML solution will come from the picture for to solve the problem. So variation algorithm to solve different problem, and surely that impact come from zero waste protocol, because clearly we know that if you know the digital twin, whatever thing is come from the picture, you understand that you can get the results of in the thing, and you can wastage is less. For example, AutoML. There are many things, AutoML, digital twin, there are many things aspect. You can reduce this number of wastage in the protocol also. I said supply chain. I said clearly that supply chain is one of the, I said TSP. I said clearly the TSP problem, NPR problem. So you can say D waves, they are already handling quantum annealing there. So they give a time and delivery, they give a straightforward method to solve for P solutions. So quantum solve for supply chain problems also. Again, energy grids. Again, I said clearly energy, very important for Industry 5.0. So integrating for renewable energy, solar or wind, based on that handling for high voltage. So the quantum can do the balancing for this real time. How they're doing? Because of quantum grids or quantum, based on the quantum sensors, give these solutions and get the good rid of all the things. Healthcare, I can get said no personalized medicines doing for this surely. And financial aspects, I not talk about financial aspects much because that's again they give for do for portfolio things, do for fraud detections, everything happening for I say portfolio and fraud detection come from Industry 5.0's main team. They're doing for QML doing for it. And then cobot again says human machine interactions applying for QML doing for much faster and doing for it. And surely again, chatbot something is cobot. So, apply for AI based kind of thing. It applying for doing well. And very interesting one is sustainability clinical, it's a chemical production also. So I know nitrogen gas is very famous for 2% of the world. You can pay more cost to go for it in the thing, but we apply for quantum level. It easily find this what energy level losing. We can easily get how much you can do it, and you can solve the problem on the real time also. Carbon capture. This is very interesting one for, and all these new results come from the VQC problem for CO2 capturing. That's very interesting one doing for QML doing, and traffic flow optimization. Very interesting one for reduce this traffic flow thing also. Yeah, so these things are applying for solve for QML based, okay? And noise problem, very interesting one. Sustainability, very interesting one. This is again, so this is a very interesting one. The current chips come from 100,000 qubits. So that means we know that the error correction is a very interesting one. Once you're done for thing, you can cool for time is very interesting and scalability very more. So the quantum scalability is not at all big question. Easily you can do for, you can scale much more. So for example, everyone talk about 1024 qubits, blah, blah, blah. But the assumption is 275 qubits enough for the world can solve all the problems. So 275 qubits. So, currently the IBM is solving for 1024 qubits. So I say 200, almost 300 qubits enough. We solve all the problems in the world. So, but the IBM doing for 3 times more powerful systems. That may be scalable, very interesting one. And how to skill gap. So maybe if you want to learn from the quantum level, you can go to physics, quantum era, CS, machine learning, domain knowledge. Based on that domain knowledge for different aspect to come from. So I put VAT because we're doing something on quantum level. And you know that ethical things, surely that PQC, I said based on that, and then human-centric development, quantum devices matter for it. So how to do it? Based on that classical age, because clearly you know that quantum computer will be cloud-based acceleration, because surely that cloud-based one thing. So need seamless for IoT edge to quantum, I mean cloud thing. How to do it? Quantum as a services. So that will come from the future. These all future aspects. Okay, quantum as a services. Okay, so this will come from, and we know that this is a one. For example, 2025. Now this is a NIQSQRA, the proof of concepts, and maybe 30th, maybe 10, maybe 1 decades, maybe the material science will be maybe will go further and further. After maybe 2-3 decades, maybe fault tolerance quantum computing will come. Maybe let's see, next 3 decades will come from. We don't know exactly. People are working on it. So there are different case study I gave you. So for I skip for you the case study. I give slides. Maybe if you anyone interesting, you can contact me. We'll give you much more understanding for to work on quantum level for machine learning. So I'll give a case study for aerospace. So 2 different case studies. Finally, I conclude because I said 20 minutes. Maybe I more than 20 minutes I took. So the summary for key taken. I said Industry 5.0 demanding for sustainability and human-centric. It's a very interesting one. And classic computing limit for limits and complex natural simulation because of they cannot do it in classic computing. So surely quantum machine learning, I think quantum will do it, but I am a computer science perspective, I go quantum machine learning. Quantum machine learning offer a path to solve this high complex problems. Okay. So we are in experimental era. Now is the time to build a IP and skills. Maybe we do it in future. Okay. So that's the thing. And this how to do it? Surely collaboration, innovation, sustainability. That's clearly maybe academic and industry make a partnership and then do for a good pathway in the future. So thanks for. I think I took extra time. Sorry for it. If any questions, doubt, please.
That is fine, sir. I think the topic, whatever you have taken, the duration is not enough. We have to call you for 1 day workshop, I think so.
Yes, 20
Because it's
minutes
a
you said.
huge topic, and every disruptive technology is actually scaring us. AI, ML, DL was scaring us. Now the quantum computing is also.
No,
So
it started 5 years before, but now is the era. Yes.
Yes. Sir, will QML outperform machine learning?
How
What's
QML?
your QML outperform regular machine learning algorithms? And do we have infrastructure for it right now?
No, no. See, for example, I can because I have no time. Your time is I can show you. No time. No time.
It's okay, sir. It's okay.
Okay. So, for example, I made it a one experimental 2023 I started, but still, classical computing is solved from 99% my image processing. But quantum thing is quantum machine learning is 0.72 also not coming. So it's very delay because of depends upon this hardware, I mean, logical qubits, many things. I cannot say now. I cannot say the answer now. Maybe future, but not now.
Okay, sir. Thank you, sir. The floor is open. Any questions? Audience, please.
Yes, so this is, this is Professor Dhananjay Sharma here,
No.
Professor of Practice. So it was really, I think you have touched a very hot topic of the industry. And I being, in the supply chain industry for 30 years, and I've joined here, I can correlate when you said the logistics and the route optimization, how challenging it is and how really the quantum can help is truly interesting. And some of the things, the takeaways I noted is maybe the first one is this paradigm shift actually from the technological upgrade to value-driven shift, what you said. It resonates well with me. These are some of the points. It was resonating. I want to just repeat that. And second thing was well-being of the worker at the center. I think that's the key here because we said the human-centric and sustenance and adapting technology to human needs and not vice versa. When you said that's really, the
Yes, yes.
point there.
Yeah,
And
we need human because everywhere firing
absolutely.
happen, firing happens, so we should be.
Absolutely. And overall, when you said respecting the production limits of the planet, because that's where, we kind of have to protect not only human beings, but the other assets, environment, all that, so that we protect, preserve, and sustain for the future generations to really, take advantage of that one. And really, the quantum is where we are looking at how it helps, because I know maybe Industry 5.0 is where we are starting some of things on the quantum side. Because what I personally feel quantum is that a lot of things we have to unlearn and relearn. Maybe that's the
Yes.
whole part in quantum side, I feel. Unlearning is the big thing here, actually, and then relearning it, a lot of things. And I hope, that should really kind of, help us really, on this human-centric and sustainability, actually. Yeah,
Sure.
absolutely. And the key point was even the collaboration and was the key here. Even from previous talk I heard, people are talking collaboration because the world is small now. We will have to collaborate our thesis, our hypothesis across and get the feedback. Absolutely. So it was great, your topic. Yeah. And 20 minutes probably is not enough for this kind of topic.
Yeah, big topic.
You
I
covered it
speaking
well.
because of 20 minutes, it's not possible.
True, sir. Very well taken. So thank you.
No
Thank
questions?
you. Thank you, sir. Any other questions?
Yeah, maybe topic is a very hard.
Yes, sir. It's I think
Maybe
it's
you can get
time.
idea. No, my motto is like I'll give you some picture. Maybe you can go back again, check with your internet and get learn. So this all topic in nowadays. That's why I want to give this topic.
Sure, sure, sir. Sure. It's really very informative and very insightful, sir. So I think I can conclude this session. We are very happy to have you here, sir. Thank you so much for your insightful talk. Thank you
Thank
so
you.
much.
Thank you. Thank you.
Thank you.
I can wind up?
Yes, sir. Yes, sir.
Yes. Yes.
Thank you. Thank you.